But on Thursday, at the start of class, we're going to have a short written quiz. It doesn't involve any computation, so no calculator, just you and your brain and something to write with. I'll give you the quiz paper, and it'll be 10 minutes. I don't think it'll actually take you that long. It's just a matter of reading through and doing some of the things that we've been doing. I'll list out this on Canvas so you can read this, but it'll cover functions and function notation, as well as our concepts of variables, parameters, and constants and the differentiation between those, and constant rate of change, generally how we've talked about change so far when one variable relates to another, and incremental increases or decreases in one causes something to happen in the other, and the associated variables and parameters that we have with those. So that's coming up on Thursday at the start of class. Today, I'm not going to talk about calendars right now. I want to continue where we left off. Let's see, we had a couple of worksheets that I posted a week ago, and we talked about one of them last Thursday. And the first half of this one, about the race car and function notation, we talked about last week, Thursday. We got through this end, and I think we started at the very beginning of this. So let me shrink this just a little bit. A little too small. There we go. So if you don't have the paper copy of this with you, again, it's posted on Canvas. It's the constant rate of change. I forget what I titled it, constant rate of change, or if I titled it something about race cars. But this is the second side of that, which is about water in a sink. And we're talking about constant rate of change for the water level in a sink as time goes on. It was a slightly clogged sink, so it's not draining very quickly, but it was draining at a constant rate with the depth changing at a rate, the height of the water in the sink or the depth of the water changed at a constant rate over time. So we were using function notation along with this, unlike when we did this just earlier. So function notation used, for instance, W of 2 equals 8 to indicate what this 8 is. You remember that W of 2 indicates the value of the dependent variable or the dependent quantity. We're talking about, in this case, this capital W of T is the height of the water in the sink measured in centimeters. So when, in this case, the W of 2 indicates T, the independent variable is 2. So after 2 minutes, according to this, the depth of the water in the sink, or the height of the water in the sink, however you want to refer to that, is 8 centimeters. Is it increasing or decreasing? Decreasing, right? It's draining. So we talked about last time that it's draining at this constant rate, or the height is decreasing at a constant rate of 1.23 centimeters per minute. So if we're noting things, and on the bottom of your sheet, which you can't see in mine, you have these notes and squares, our constant rate of change relationships that are key to everything that we're doing. dy equals mdx. Changes in our dependent variable are a constant multiple of changes, variations, incremental additions or subtractions, whatever's going on, however it might be occurring. They're a constant multiple of the values of the independent quantity. So dy equals mdx, and then there's this y final equals y initial plus dy. And since dy is also a multiple of dx, oops, sorry about that, we could talk about, instead of y initial plus dy, I could talk about y initial plus mdx as well, mean the same thing. So back to the top of this page, maybe. All right, so we have, for the whole page, water is draining at a rate so that the height changes by 1.23 centimeters per minute. In the first question, we've got, we want to write a computation and an expression with function notation to indicate the change in the height of the water, how much it decreased during the time interval 2 through 6 minutes into this draining fiasco. We started trying to drain the water. It's not going very fast. So just as a quick note here, it says write one computation, one function expression, or function notation expression. Change in the height of the water in the sink. What type of quantity is that? Is that a rate of change? Is that a change in the independent variable? Is it a change in the dependent variable? Is it a value of the independent or dependent variable? Is change in the height of the water in the sink. Thoughts? Yeah. Yeah, we're talking about the change in the dependent variable. So thinking about those letters that are in the box at the bottom of the page, what symbol or expression or symbols go with change of the dependent variable? dy. So this is asking us to write an expression for dy. And it says like computation and expression with function notation, but regardless of how we're writing it, the concept that we're getting at here is that we're trying to express a change in this dependent quantity. So the information that we're given, besides that we call the relationship W, and there's this 1.23, the relationship specific to 1A is something about between t equals 2 and t equals 6 minutes. These are values of the independent quantity. So how are values of the independent quantity here, the time that's elapsed since we started trying to drain the sink? These are values of maybe x in terms of those general letters at the bottom. So what is it that we are going to want to do with these to help get us towards this dy? Any thoughts on how 2 and 6 are related to this change in the dependent variable? Well, what's one thing I'm going to do computation-wise? Subtract, right? If I subtract those two, what does that, just the subtraction on its own, correspond to in terms of expressions in the bottom box? If I do 6 minus 2 or something and I get 4, that's 4 is a value of what? Dx, right? Remember, 4 isn't a value of x. It's not an amount of time since we started draining the sink. 2 and 6 are those. This 4 is in terms of those general letters, dx. Now, in this case, we were actually calling those t, so we could talk about dt and dh instead of dx and dy, but just to refer back to those same general concepts, we've got a change in this independent variable's values, so an elapsed amount of time, 4 minutes have gone by, dx, and we want to find dy. So dy equals mdx would help me with those, so we can find a value of dy. Now, in this case, it's not actually dy, it's actually h is the name of the dependent variable, so I could, in reality, the specific question, it's find a value of dh. What computation do I end up writing in order to compute the value of dh? Yeah? All right, negative 1.23, that's our rate of change that's constant throughout this situation, this m value times 4 dx. So dy or dh, to use the letters of the exact problem, is dh is negative 1.23 times 4. This is finding a change in the dependent variable, or how much the dependent variable's value has varied over a period of, in this case, 4 minutes of time. But this comes from dy equals m dx. The corresponding amounts of change between time and depth are off by a factor of negative 1.23. So we can multiply this out. Now, if I wanted to write something similar to this using function notation, representing this instead of writing out all the specific numbers, I've got 6 and 2 here, and this is my m, but what is dh in terms of function notation? Remember, the function name is w, capital W. So it would still involve, there's different ways we can express an essay. I think we talked about this in terms of a race car multiple times. Yeah. W, what was that? $15? Oh, W of t. So we don't, W of t is the height of the water in the sink. And we're looking for how much it varied by over a period of 4 seconds, right? And it's not just any 4 seconds, although it's a constant rate of change, so it'd be the same over any 4 seconds in this case. But if I want to express somehow using function notation the change in the height of the water in the sink over this time period, if you remember what we did with the race car, it was a subtraction. Right, W of 6 minus W of 2, final minus initial. W of 6 represents the height of the water at the end. W of 2 represents the height of the water at the beginning of this particular interval, 2 through 6. This would come out negative, agreed? Because W of 6 is going to be less than W of 2. That's okay. We don't want to know just the size of the change. We want to know in what direction. So this expression with function notation is equivalent to that, like y final minus y initial. We talked about that with when we were talking about one variable at a time. But keep in mind that this tells us a lot of things. This W of 6 minus W of 2 tells me that I'm computing a change in the dependent variable, but it also tells me which change. So it's a constant rate of change, so any 4-second period within this situation would have worked out to be the same value, negative 4 point whatever that is, 4.92, okay, thank you. Negative 4.92 centimeters, but this is specifically saying that I've got the height at time 6 and the height at time 2, so I can see which 4 seconds it is, in addition to the fact that it's 4 seconds. So if I just say DH, that doesn't tell me when this variation occurred, when the decrease occurred. If I say W of 6 minus W of 2, I can say, oh, well, this is the decrease in the height that occurred during that specific time interval. All right, so there's multiple ways you can write things when you have a function, and when you have constant rate of change, there's a variety of different ways you can express the meaning that you want. All right, so look at 1b. So now suppose W of 2 equals 8. What is that a value of? W of 2 equals 8. Those are values of height, right? So that's a dependent variable value. And as related to part A here, W of 2, that's at the beginning of the interval. All right, so this is a dependent variable value at the beginning of something that we're talking about here. This question, part B, asks to write a computation for W of 6, a dependent variable value at the end of the same time interval. So thinking about other things we've written, y initial and y final, we want to write a computation for y final. Oh, well, based on the stuff in the box below, y final is y initial plus dy, or y initial plus mdx, just using the general xy letters. These are actually h's and t's in our case. But y initial plus mdx. Oh, okay, so y initial, our height started at 8 and then decreased by this right here, 4.92. So we could multiply and subtract if we wanted to, or we could to write a computation for y final. I just need to fill in the blanks. These are all things we've either just been told or already worked out how to write them. So I could say that W of 6 is W of 2 plus mdx, or W of 2, which we know, 8, plus a negative or minus 1.23 times 4. So this is just the expression from above. So part A was asking for an expression for that incremental decrease, that decrease in the height of the water in the sink during that 4-second time interval, whereas part B was asking for, so what's the new height then, if I know where it started at? So if I were to change, suppose W of 2 equals, and I put a different number here, the only thing that would change is that, right? So in terms of this 8 could have been a different number. All that affects is what I write in that next line, that initial value. All right, so let's take a look at number 2. And I know that you've had this for a while, so I'm going to let you take a look at it with neighbors. Compare notes on number 2. See if we can come up with, again, sort of for A and B. For A, a computation and an expression with function notation. And there's varieties of combinations of ways you could write this. And then part B, given some sort of value, write something else. So if you notice, compare 1 and 2, they're asking kind of the same type of question, just with fewer specific numbers and more general stuff. So we've got an interval for number 2, starting at t equals 4, that lasts for k minutes. So let me ask this question. During that interval, how much time passes between time 4 and time 4 plus k? K minutes, right. It's not 4 plus k. 4 plus k is the time at the end. 4 is the time at the beginning. So the length of that interval is k minutes, as it says actually in the sentence. So this one describes the interval in terms of how much time goes by. So we've got, let me get this pencil back on again, an interval of k minutes. So specifically, it's the k minutes that start at 4 and go to 4 plus k. In this situation with a constant rate of change in a sink, if it was time 3 through 3 plus k, the same amount of variation in the height would have occurred, correct? Because it's constant rate of change. In any k minute time period, the same variation in the height from the beginning to the end would have occurred, as long as it's a reasonable k, so that the sink doesn't empty in the middle of it. So if I want to write a computation, it's not going to be all numbers, but just a simple expression without function notation for how much the height of the water changes during that time interval. That's, again, an expression for dy, right? mdx. So what is our mdx expression this time? Right, negative 1.23k. Now, in reality, it's not really a y for this problem. To use the letters of this question, it's an h. It's the variation in the height of the water in the sink. W is the name of the function. H was the dependent variable value. So dH is negative 1.23k. This computation, regardless of what k is, would give us that. So what about in function notation? How could I use function notation, function w, to express something that would have this same value? Or instead of writing dH, how could I use function notation to express precisely which variation we're talking about? Yeah. Final minus initial. W of 4 plus k, the height of the water of the sink at the end of the interval, minus the height of the water in the sink at the beginning of the interval. So much like the race car questions that we did previously, final minus initial, but because it's constant rate of change, we also can just use the length of the interval times that rate at which the change occurs. All right, so again, part B, just a step beyond, doing one additional computation. Suppose that W of 4 is 5.7. That, like last time, is the height of the water in the sink at time 4, at the beginning of the interval. So that's a y initial, and I want to find a y final. So y final, W of 4 plus k, would depend on this W of 4. I'll write it symbolically, plus mdx, or in this case, negative 1.23k. Or instead of W of 4 here, since we have a number, we could write 5.7, and then I'll just write minus 1.23k. There's a variety of different ways you could express this, but this computation follows our general premise. How do I find the final value of y? Since final minus initial gives me that variation or change, then the final value is the same as the initial plus, or in this case minus, that change, since the change in this problem was negative. All right, questions? Yes? So either of those, so write an expression for the water's height. Since we actually, this is the one above here, this is kind of has some more symbols in it. Since we're given a value for W of 4, I could write this instead, but either of these is an expression for it, as opposed to, what I mean by an expression is write out something that will give us the height, but this one isn't necessarily computable because I don't know what K is. This is just in general, for any k minute period, and if I told you a value of k, we could get a number now. But just an expression, meaning you don't have to find a numerical value for it, but some way to demonstrate how you would compute this. All right, so number three, kind of the same thing, more and more general. So if I wanted to look at, here we go, an expression using function notation for the variation in the height of the water during any general interval starting at t equals 5. So think of it as going from 5 through t. And then you could even imagine, well, what happens as t starts maybe at 5 and gets bigger and bigger and bigger, and think of this as a demonstration, if we were to graph this, of what happens to the height of the water in the sink as time increases, and you can watch it increasing. But any general interval starting at t equals 5, thinking about what we did with the car, that's 5 through t. You can think of it as ending at t, but we can let t be whatever we want. The way it's written, it seems like t should be larger than 5, but it doesn't even have to be. Any general interval starting at t equals 5. So, like the previous questions, we're looking for the variation in the height of the water during this interval. Not what is the new height, but just the change in the height. So that change in the height depends on, well, mdx, right? That's our dependent variable that is changing by a multiple of the length of this interval. So negative 1.23 times what? T minus 5. For any value of t, wherever that might end, if I want to know final minus initial, that's t minus 5. So if t was 5.1, that incremental increase in elapsed time between the beginning and the end of the interval would be 0.1 minute. Whatever it might be, this t minus 5 would compute how much time has elapsed since the beginning, since t equals 5 in this case. All right, so suppose that w of 5 equals lowercase h. Yeah, oh, question, sorry. Oh, yeah, sorry, I didn't write the function notation version. Yeah, so any thoughts? How could I write the function notation version of this expression? Yeah, w of t minus w of 5, the height of the water at whatever time t, minus the height of the water at time 5. That would give me the variation in the height of the water during that time interval. Thank you, sorry I skipped that. So if w of 5 is h, lowercase h, and I want to write an expression for the water's height at the end of this general interval, that is, I want to write an expression for the height of the water at time t, and I know what this number is, and I know what dh is. Here, y initial plus dy. Converting this into this particular problem, initial value was w of 5, which was, well, I can write w of 5 or lowercase h. dy is this mdx, or to be specific about this problem, negative 1.23 times t minus 5. So our final height at any time t, we can base on an initial height and the variation since that time, which occurs at a rate of 1.23 centimeters per minute for each minute after time 5 has passed. So each of these is just a slight variation on the last, but keep in mind these two relationships down here. When you're going through homework, when you're reading the textbook, when you're reading expressions about related quantities and how one causes a change in the other, think about whether the amounts being described or the expressions that are written are representing like a dy, a dx, a y initial, a y final, a rate, that constant rate of change m. Think about what each piece is representing so you can figure out what you have and what you're trying to determine. Question?
More practical question. Are you okay with us leaving it in that form, or do we need to simplify it any further?
No, you can leave it like this. So written in this last form, she asked whether we need to simplify this, because you could distribute negative 1.23 times this and that, and maybe it looks neat to not have parentheses, or if you had like terms, but if you can see from this, you can maybe identify what's going on. By having it in this structure, you can see an initial value of 5 that goes with h. So this is an initial value of my dependent variable, and I incrementally change by this much. So here's my initial x value, final x value, initial y value, final y value. So you can identify kind of parts, what's going on, and see this rate, and talk about, well, where did, because if you multiply this out, there's going to be this negative 1.23 times negative 5, and it's like, all right, so what does this 6 point something have to do with anything in this problem? Well, if you simplify, it'll come out to something like that, but if you don't, you can see incrementally, and thinking about if I were graphing over time the height of the water, so the height measured in centimeters, time measured in seconds, what I have here is like, well, I know that at time 5, there was a height lowercase h. And past that, I know that the height of the water was decreasing at a rate of 1.23 centimeters per minute, meaning, easy way, after 1 minute, the height would be 1.23 centimeters lower. But after any number of minutes from this point in time or from any other point in time, the change in the height, which would be a decrease, the decrease in the height would be 1.23 times however many minutes had elapsed, and the height change would be measured in centimeters. So that is, I can think about measuring it's dt or dx this way, and dh here. I could let time vary a little bit more. I could let it vary to any amount, because this is a constant rate of change. So incrementally increasing time from 5 or from anywhere else, the rate of change is always going to be the same one number. Question? Let's see. W5 was this lowercase h. It's not going to be the same as that, but h would represent some number, which supposedly is the height of the water at time 5, right? So you can imagine it's this height. If I were to go through and simplify this by distributing, I'd have w of t equals, I'll put variable terms first, negative 1.23 t, and then there'd be an h and a 6 point something, right? 6.15. So an h plus 6.15. In terms of this graph, h plus 6.15, thinking just algebra stuff, that'd be your vertical intercept, or that would be the height of the water in the sink at time 0, h plus whatever. So that's that going backward by 5 seconds towards 0, how much higher would the water have been? And that 6 point whatever, that's the how much higher. Because I don't know what h is, right? All right, so let's move on from this. Clear this off, boom, gone. But keep in mind, again, like I said, keep in mind when you're reading these questions, think about what they're asking you for and what they're giving you. So let's see, is this going to cooperate with me? So just kind of recapping what we did, combining our linear function notation or function notation with our constant rate of change or linear change. So just as a note, all the paper shuffling, getting out your notes to write stuff down. If you want to take notes in class, I encourage it, but keep in mind, you don't, if it distracts you from paying attention, you can, please feel free to sit and just absorb, because I do post the videos for this later, so if you want to like write down notes later, you can go back and view the same slides again, because I know like some people, like I write while I'm listening, and then I can look at it later. But I know sometimes if you prefer to just look and absorb that way and then write it down later once you've organized it in your head, if that works better for you, please feel free to do that. I'm not going to yell at you for not taking notes. If you want to do that later, there are 21st century options for doing so. So, in any case, going back to where we started kind of at the end of chapter 1, beginning of chapter 3, once we got past just vocabulary stuff. So, computing change or variations in quantities that do vary. We can look at change in a single quantity. So we talked about just like the memory on your phone and adding a program, subtracting a program, and how much memory is being used and why it takes so long. So you can just do single changes to find the variation between values at different stages. We can just final minus initial, and we can represent that if y is the variable assigned to that, and we can call that final minus initial, that dy. Or whatever letter you're using, z's or x's, pick your favorite, which obviously can be rearranged. Y final is y initial plus a change. If you have two quantities where one causes the other to change, covariational relationship, then if you have that constant rate of change, you can use that constant multiple to get from one quantity's amount of change to the other quantity, the other related quantity's amount of change during a related time period over a related change in values, whatever it might be. Time doesn't have to be a part of it, but if you do have two variables, you can talk about a dependent and an independent quantity, one causing a change in the other. Sometimes they're just about equal partners, and you could write it either way, just as sensibly. But dy equals mdx. Change in one variable is a constant multiple of a change in the other. Or likewise, you could rearrange that to be the rate of change is the ratio of those two changes. And we're going to talk about estimating values of constant rate of change in situations where it's not precisely constant, but it's pretty close. We talked about zooming in on graphs and they look essentially linear, and we're going to talk about that more in detail on Thursday. But to find that constant rate, if you have the corresponding variations in two quantities, just the ratio of those, the dependent divided by the independent amount of variation that correspond to one another, gives you that m, or that constant rate. So, visually speaking, we talked about if we only have one variable that we're dealing with at a time, like number line sorts of graphs. And lots of times we don't even think about graphing if it's only one quantity that we're measuring. Does it get bigger? Does it get smaller? We go left, we go right. You could draw it vertically if you wanted to. But if I have an initial value of some quantity that I call y and a final value, then dy is the distance between those in this graph left to right. So I could also imagine not necessarily having just two fixed spots, but thinking about starting from somewhere and letting y increase from there. I just happen to pause here and take a note of how much has it increased so far on its way to continuing increase or decrease. We could also go back the other direction, become smaller. If you have a change in two related quantities, and let me just scoop this out of the way, then we can see that ratio, and this is kind of what I had drawn for the height of the water in the sink. As time progressed, we had the height of the water remaining in the sink decreasing at a constant rate. So visually speaking, if I have these Cartesian coordinates, these xy coordinates, I'm going to see something that looks like a line that is, in this case, going up at a constant rate from left to right. The one we just did was going down at a constant rate from left to right. Either way, that constant rate represented by the fact that I could draw, I could measure between two spots in here, any two spots. And let me just scoot this a little bit. Oop. So if I were to pick 2 points that are a lot closer together, but be able to measure the vertical and horizontal change, or the change in the independent horizontal change and the change in the dependent vertical change, the ratio of those two little tiny changes there would have to be the same as the ones that are drawn there already. And not just for those two, but pick any points I want. And I can use the same starting point and a different ending point. Any amount of change starting from anywhere in one variable has to be matched by a multiple, using the same multiple every time when we're talking about constant multiple of change. A multiple of that in the other variable. So dy has to be mdx no matter where or how big this small change is, this change in the independent variable. This has to be the same multiple every single time. All right, let me get this off of here. All right, so we were talking about a flag example earlier on. We had a flag that was being lowered by Marines in the ceremony at a nice, slow, even rate. We were talking about that before we talked about function notation. So, in addition to adding in some function notation here, eventually, not on this page, I'm going to put up a few questions. I'm going to let you think about them. But what I want to point out just with this first one is, so here's the first question. We've got a soldier lowering a flag, constant rate, 0.75 feet per second. The variables are defined, what quantity they're measuring, and what units they are. So X is measuring elapsed time in seconds. So elapsed since he started lowering the flag. And Y was the height above the ground measured in feet. So this was all from last time. If the flag began at 110 feet above the ground, how much is it lowered after 3.72 seconds? Make sure you're careful about what it's asking for. So again, when you're reading these, just like we did on the worksheet, if the flag began at 110 feet above the ground, how much has it lowered after 3.72 seconds? In terms of Y final, Y initial, dy, m, dx, what is this 110? This 110 feet? Yeah, that's a Y initial. So this is very stubborn with me today. All right, let's try this again. So this is Y initial. How much has the flag lowered after 3.72 seconds? What is this A question asking for? A value of dy. Now, dy could be figured out by, y final minus y initial. But that's not what we've got here. We want to find dy. What is this 3.72 seconds a value of? I want to find dy, and I'm given dx. Well, dy and dx are related by this. I need one more ingredient in order to be able to find dy from dx. M. And, well, it's kind of here. It's lowering, so m is negative 0.75 feet per second. So that 110 feet above the ground, in terms of this part A, that's irrelevant. Might be useful for part B, which you haven't seen yet. But just keep in mind, you don't have to put all the numbers in and do something with them. Make sure you're careful to read what it is you're supposed to be answering. So just find dy given dx, and up above for the whole question, this parameter value for the rate, m, negative 0.75 feet per second. So what about for part B? What is its height after 12.87 seconds, it being the flag? What is this asking us to find a value of? What symbol would express what we're looking for? Yeah, this is looking for a y final. And that 12.87, why this keeps doing this today. So we want to find y final. After 12.87 seconds, well, after 12.87 seconds, since the flag left the top of the pole. So that's our dx in this case. So part A and part B, we have dx's for both amount of time that's gone by. In both cases, these are both actually values of x and also values of dx. Change in time since the beginning, but it's also just the incremental amount of time that's gone by while using this rate, so that's okay. But we can talk about what the height is and what the height has changed by. So just make sure you're careful about distinguishing between those two. So in the first case, what's the computation that I need to do in order to find how much the flag has lowered after 3.72 seconds have elapsed? Just MDX, right? So it's negative 0.75 times 3.72. So this is our MDX. Find dy given dx. So it comes out negative, meaning the flag's height is lowered by however many this comes out to be, 2 point something feet. Now, if you're writing a sentence about this, and the question was how much has the flag's height decreased or how much has the flag's height lowered after 3.72 seconds, I don't need to say it's lowered by negative 2 point something feet. I just want to say it's lowered by 2 or it's decreased by 2 points, whatever it comes out to be, 2.79 feet. So it's decreased by 2.79 feet, or it's lower by 2.79 feet. I don't need to put a negative in there when I'm using that negative word, or that word that indicates decrease. The negative when we're doing computations indicates decrease, but make sure when you're translating back and forth between math and English that you don't have too many negatives in there and make a double negative for yourself. All right, so put up another one while we're at it. What's the height after 12.87 seconds? We still have an MDX, but this time we just have a Y initial that we need to append onto that. So here, I bet it's going to pop back again. Yep. So if I want Y final, I need to have Y initial plus MDX. So that's our 110 is important here. 110, and then it'll be plus a negative, so minus 0.75 times 12.87. And we could work that out, but this expression, numerical expression, we could compute that, and that would tell us the height after the 12.87 seconds have passed. So our constant rate of change for 12.87 seconds would have decreased 110 feet height down to something lower. All right, so here's the part C that's kind of more like the part B or C at the bottom of the last worksheet. Describe the flag's height Y after X seconds for any X between 0 and 100. What the 0 to 100 is, eventually this flag is going to be low enough and you're going to stop lowering it. You're going to stop this constant rate of descent and start folding it up and doing something cool. But if I want to describe the flag's height Y after X seconds have passed, if X is somewhere between 0 and 100, I'm looking for the height after time has passed. So this is a Y final again, just a less specific Y final than the last time. All right. So I could write Y final as Y initial plus MDX. So our Y final, we're going to call this Y. Flag's height Y after X seconds for every X between 0 and 100. So what was the flag's height initially? Y initial? 110. That applies to the whole problem, 1, A, B, and C. And then M, constant rate of descent the whole time, negative 0.75. I need to express dx. Any thoughts? Yeah, so x. Now I could also say x minus 0 if you want to think of, oh, this is an interval 0 through anytime x, just knowing that x is something not past 100. Just in terms of sensible domain for this problem, that's why there's that 100 there. But you could talk about final minus initial to get this dx, because we're talking about since the beginning, since the flag was at a height of 110, which was at the beginning, at time 0. Here's my x initial, x final. Final minus initial gives me dx. Here's my y initial. So all the pieces are in there. With this one, as it's stated, because this is starting at a height of 110 feet and measuring the change relative to where it was at the start at time 0, there's some pieces we can leave out, like that -0. You don't have to write it. But keep in mind that that x represents then how much the height has changed since the beginning, in addition to, or how much time has changed since the beginning, in addition to just how much time has gone by in the question. But it's relative to or related to this 110 feet. All right, so to make this more interesting than starting at the beginning, on another day, strong wind tangled the chain at first, but by 20 seconds into the ceremony, they're able to keep that constant descent rate of 0.75 seconds, or 0.75 feet per second. So, in other words, thinking about me continuing clicking on things, if I was kind of track the height of this flag as time goes on, maybe it started at that 110 feet, but we're trying to get it down and it got tangled, stuck for a little while, and then after that we were able to descend at a nice constant pace. But for a while at the beginning it was a little mess, so it was blowing around, so there wasn't a constant rate the whole time. But starting at 20 seconds in, we're able to keep up a constant rate of descent. So thinking about this, if the flag was at 104 feet above the ground at this time 20, how much would it descend in the next 3.72 seconds? And I'll put up a couple other questions as well. Kind of similar questions to what I asked last time, but we have different situational information at the beginning. Some parts will change, some parts might not. And don't worry about doing the multiplication, subtraction, and that sort of thing. Just write out what computations you would need to do, or what expressions you could write if there's something more general. All right, so got a flag at 104 feet above the ground at time 20, and from then on, it starts decreasing at a constant rate. It started at 110 20 seconds ago and was kind of, maybe had to raise a little, get it untangled, lower it a little. Whatever happened, happened, but now we've got a constant rate from here on out. So to answer question A, how much would the flag descend in the next 3.72 seconds? What do you need to do to compute that? Right, dy equals mdx. So this is the same first question as in question number 1 here, 3.72 seconds. Doesn't matter what the starting height was, it's just we're looking for, in this case, the next 3.72 seconds instead of in the previous question, during the first 3.72 seconds. But during any 3.72 seconds while constant rate of descent is happening, we just get to do our negative 0.75 times the amount of elapsed time, 3.72, which is at 2.79 seconds, or feet, that it descends. So this was during the next 3.72 seconds. So the first 3.72 seconds during which it had a constant rate of change. Question B, what would be the flag's height by this time? That is, what's the flag's height by 23.72 seconds into the ceremony? What do I need to do for this one? Or what is it I'm looking for here, symbol-wise? Y final. So I need a y initial plus dy, and we just figured out dy. It's asking about the same scenario. Going forward 3.72 seconds. And over that incremental addition to time elapsed, the height goes down by a little bit, about 2.79 feet. So the flag's height is less than it used to be. Y final, y initial plus dy, and it's the dy we just calculated. It's the same amount of elapsed time that we're talking about at the same rate. So just 104 minus 0.75 times 3.72. So the height at this slightly later time, we can compute, like 20-ish feet. So what about for part C? What would be the flag's height at 45.31 seconds into the ceremony? I'm still looking for a Y final, right? How much more final is it? How much later is this than anything? We've got a couple different ways you could compute this. Yeah. 25 point. Right, yeah, 45.31 minus 20, right? So this is 45.31 seconds into the ceremony, but we only have information about where it was starting at 20 seconds into the ceremony. So we'll start from there and go forward in time, downward in flag height, up through some point in time that is a bit later. So instead of worrying about 23.72, if we worry about, well, not worry about, but think about 45.31, we've got a new dx we can compute there, and the change in y over that larger interval, which contains all one rate of change, all negative 0.75 feet per second. We can get our y final, 104 minus 0.75 times, and we could either write it out, or this one's pretty easy to subtract, but 45.31 minus 20. X final minus X initial, or this is all dx. All right, how do we feel about this? Not too bad. Your homework, some questions are more along this lines where there's several of them that go together. Read through the textbook. You'll see some more examples. I do want to show you, let's see, we've got, what, 12 more minutes? Yeah, we can do one more. Assuming this is going to let me click from here to there. Skip that one. Different scenario, because I'm tired of flags. not in general, but tired of computing with flags. So laptop batteries. As yours is going down through the period of this class, hold on, we still got 15 minutes left. All right, suppose you open your laptop during class to take notes. 35 minutes after class started, your laptop battery has a 41% charge. 75 minutes after class has started, we have a 28% charge. So you're hoping it makes it to the end of class. This is a 75-minute class, so in this case, you'd be fine. But the percentage charge P, let's use that as a dependent variable, changes at a constant rate with respect to the number of minutes since class began. T, we'll use for that, call that the independent variable. So without doing unit conversions or anything like that, just the natural units that would appear for this rate of change of P with respect to T. Think about what units would apply to that rate. See if you can compute, as a fraction, decimal, whatever, the constant rate of change of P with respect to T based on this, assuming that it's a constant rate. We can use it at least as an average, but probably fairly constant over a short period of time, not near the end of your battery life. And then a third question, during any 6-minute time interval during the class, by how much would the battery's percent charge change? By how much would it vary? By how much would it, in fact, decrease? That's what we're talking about. So take a couple minutes, compare notes with a neighbor. Make sure you think about the two key relationships we have for constant rate of change. All right, so units on our constant rate of change. Just think about this without doing any like changing to units other than what are in here. If I have a rate of change of P with respect to T, just using the units from the problem, what units would that be? Percent per minute, yeah. We don't want to talk about, we could change it to percent per month or something if we wanted to, but yeah, P with respect to T, the key part of that is if it's change in P with respect to T, that's P units as the primary, the top part of the rate, and with respect to T, that's the per T, per time unit then in this case. So per, we had minute. So we'd measure this without doing any unit conversions. The natural units to have this within based on this problem would just be percent per minute. If we wanted to do percent per hour, percent per day, something else per second, we could do that, but don't have to. So the change in the battery charge percentage per minute of class. But again, it doesn't have to be incrementally 1 minute at a time. You can talk about for any number of minutes that have elapsed up to the end of class. How much percent-wise the battery would change is that constant multiple. What's the value for this? Fraction or decimal? 0.325%. Do we agree? But we're missing one small thing. Yeah, it's kind of important. It's a small thing, but it's important. Negative, yeah, it's decreasing. So negative 0.325%. So not 32.5%, just 0.325%. About a third of a percent per minute, or about every 3 minutes we lose 1% charge approximately, just estimating. But if you want that as a fraction, you can do that as well. That was a decrease of 13% charge over a period of 40 minutes. 41% down to 28 between time 35 and 75 into class. So where those numbers come from, that's just the individual final minus initials divided. P's divided by T's to get the rate of change of P with respect to T. All right, so during any 6-minute time interval during class, just picking 6 at random, it's not that it's pertinent here for something mentioned earlier, by how much would the battery's percent charge change? What would you do to find that? Yeah, 6 times negative, whatever version of that you want, negative 0.325 or negative 13 over 40. So we can do that computation. Comes out to about negative 1.95. It's not about, that's exact. So that would be the negative indicating decrease, or the battery charge decreases by 1.95%. Can you see the decimal parts of a percent charge? No, you cannot. So we'll just say that that's how much it's decreased, if it's decreasing at this constant rate. All right, so I'll leave the scenario at the top there. So here's a different scenario. Suppose we want to describe the percent battery charge and its change between time 35 and 48 minutes into the same class period. So same M, same battery charge, whatever. And I want to know how much did the percent charge change during that time interval, and then what's the total battery charge by time T equals 48. Now we have a couple of different values up at the top that you could work from in terms of finals and initials and things like that. But see if you can write an expression for, like write out the numerical computation or symbols otherwise that you need to express dt for this situation that's in black here, dp, and then p final. All right, so let's talk about this a couple different ways, but dt, asking for how much time we're interested in, look at what the time interval we're looking at, how long it extends. So in the original, when we computed the constant rate of change, we had a time interval that was from 35 to 75 minutes into class. Now we're just looking at 35 to 48 minutes into class. So part of class, but still within that interval that was mentioned above, so still legitimate to use the same M. what's the value of dt that we're looking at here? Yeah, it's just 13. It's just this 48 minus 35. Let's see if I can get this to go. Nope, of course not. I have to update this or something. But yeah, 48 minus 35. So 13, that's minutes that have gone by while the battery is discharging at the same constant rate, right? Yes. Oh, so we don't have any values for like any other symbols for these, but just 48 minus 35 gives us 13. So dp, and I'm going to insert some function notation in just a minute. dp would be the corresponding decrease in this case in the battery charge during that time interval, which it doesn't matter that it's specifically this time interval from 35 to 48, but just that it's 13 minutes long, since we've got a constant rate of change. So our same rate that we had before, negative 13 over 40, or negative 0.325 times 48 minus 35, or times 13. But this is our MDX. If you wanted to write an expression for this, I guess you could say like it's an x final minus x initial. If you want to write something like that, or t final minus t initial in terms of general setup. This is our MDX. And p final, this is where we've got some options in reality. I want to talk about p initial, the percent charge at some point in time, plus how much we've changed away from that point. We just worked out between 35 and 48 over that 13-minute period. It decreases by, like any 13-minute period, 0.325% per minute for every minute. So our initial percent charge is based on the initial that we used here. So if this x initial is referring to this time 35, then my percent initial better refer to the percentage at time 35. So that was my 41% charge. So if it helps, draw yourself a picture. There's a lot of numbers and which ones correspond to what. Two-dimensional graphs are good for that. You can see which values correspond to which others and see the patterns and make sure you're not accidentally adding instead of subtracting, something that visually speaking you might notice right off, but if you're just doing a bunch of computations with weird numbers, you might not notice. But if I'm thinking about time and my battery percent charge, I know that at time 35 minutes into class, we had a 41% charge, right? Yeah, 41. And it's going downward at a constant rate from there, such that I know there's a point later at time 75, but for this question, I just want to know what's going on by time 48, which is 13 minutes later. And the ratio of changes dy and dx, or in this case dt and dp, is this negative 0.325. So I've got 13, and then this change is 13 times negative 0.325. So you can measure those changes and see which goes where. So just as a note, if I wanted to use function notation, suppose that instead of just calling this vertical value p, let's say that p and t are related by the function b. P is a function of t, and that function's name is b. If I wanted to talk about p initial here symbolically, that kind of clarifies what's going on. Oh, this 41, that's b of time 35. Or this p final, that's b of, which final am I talking about? 48. So when you use that function notation, it's easier to specify, well, which final relative to what, initial relative to which. When you use that function notation, allows you to identify which point in time, what independent, dependent variable coalescence are we talking about. All right, so again, quiz at the start of class on Thursday, so don't be late. I'll post the topics on Canvas that I mentioned earlier, so you can be sure to be ready for that. I will see you then, if not before.
the topics on campus, will that have all the
Yeah, I'll put that up like in just a minute.
Oh, yeah.